So, can anybody tell me what we're doing? It's not an easy question. Can anybody tell me what we're doing? Not an easy question. If you're able to answer this question, I'm not going to give you a point, but I'll be kind of impressed. Anybody? Mariah.
Are we like finding matrices or not like we're changing bases, but like to go between vector spaces?
Yeah. So we're finding matrices. So remember the setting. Once you think of the setting, you'll start remembering. So the setting is that you've got a linear transformation between two abstract vector spaces. For example, remember differentiation between P3 and P2, or Pn and Pn minus 1. Okay. And then we're finding a matrix that somehow represents everything there is to know about this linear transformation. Right? The matrix is some sort of reflection, some sort of very complete reflection of this thing here. Okay. Right? So. Can anyone give a little bit more detail, or let me do it. So remember, the setting is that you have E1 through Vn, a basis of V. You have F, W1 through Wm, basis of W, right? Okay. And then once you have those things, remember, once you have bases, then you have the coordinate vector maps, right? Every time you have a basis, you have a basis of a vector space, then you've got the coordinate vector map, right? So we have what we were calling P, the coordinate vector map, right? So P takes some vector and gives you back the vector. The coordinate vector map with respect to the coordinate vector with respect to E, right? And over here we had something that we call Q, which was the coordinate vector map. Q of W is going to be W with respect to F. Right? You get the coordinate vector there. Okay. So there's a way of getting from here to here. And remember what I said, these guys are isomorphisms. These guys are actually invertible maps, right? Because they're one-to-one and onto, right? These guys are P and Q are one-to-one and onto, so they are isomorphisms. Okay. Just to wake you up a little bit, if I take V1 here, right? So V1 is the first guy in the E basis. What is P of V1? So just to warm up exercise, what's P of V1? Right. So that's the coordinate vector of V1 with respect to the E basis. Okay. So think for 30 seconds. If you don't get it in 30 seconds, then there's no point. No, I'm joking. Okay, anybody figure it out? What is it? 110. What is it? Well, you get the coordinate vector. How do you get the coordinate vector? You take this guy, you take the input and express it as a linear combination of the basis elements. And then you take the coefficients that give you that combination. Right? So how do you express V1 as a combination of these guys? Well, V1 is the first guy there. Right? So it'll be 1, 0, 0, 0, 0, 0, 0, 0. Right? Because V, right? Remember how do you get it? You take the thing that you're trying to get the coordinate vector of, and then express it as a linear combination of the basis elements. Well, it's going to be 1 of the first guy plus 0 of the second guy plus 0 of the last guy. right? And then you use those coefficients as your vector, right? Everybody okay? Right? That's what you do, right? You take your guy, express it as a linear combination, and use the coefficients as your vector, right? What if I say P of V2? What's P of V2? It'd be 0, 1, 0, 0, 0, 0, 0, 0, right? P of V3, 0, 0, 1, 0, 0, 0, 0. So what you get is that the coordinate vector Vi with respect to E is going to be E sub I, right? The standard basis element, right? Right? V1, the coordinate vector of V1 is E1, right? The coordinate vector of V2 is E2, coordinate vector is et cetera, et cetera. Okay, et cetera. Yeah, comment.
Sorry, I'm a little stuck on why V1 becomes like 1, 0, 0, 0.
Well, remember how you get the coordinate vector, right? You say, take your thing and express it as a linear combination of the bases, right? How do you get the coordinate vector of an element? Well, you have to express V as C1 V1 plus Cn Vn, right? And then you use those coefficients. Use those coefficients as your coordinate vector, right? Well, V1 is one of these elements, right? So it's going to be V1, I'm going to express as 1 V1 plus 0 V2 plus 0 V3, et cetera, right? So what are my coefficients going to be? 1, 0, 0, 0, 0, 0, 0. Okay. Is that clear? Anybody else? Okay, so that's just to warm you up. Think about this thing. Okay, so right. Okay, so remember what we're looking for. We said there is a matrix A, right, such that this map here could be filled in, so that this diagram could be filled in and it would commute, right? Such that the diagram commutes. In other words, if you take T of some vector and then hit it with Q, you get the same thing as if you took that same vector, hit it with P, right? You took the same vector, hit it with P, and then went across by multiplying by A. Right? Okay, so we're looking for the matrix that makes this happen, right? We're looking for the matrix that makes this happen. Okay. Okay. So one way of thinking about this is that, you're looking for the matrix that does, when you multiply by it, it does exactly the same thing that T does in going from V to W. Okay, it's like a mirror reality. Okay, and you're looking for the matrix that does from Rn to Rm what T does from V to W. Okay, so it's like a parallel world or something. Okay, so how do we get that matrix? How do we get A? So right, how do we show A exists? Well, we construct it. So again, we're gonna make the A that works. we want A such that if you take TV followed by Q of TV, you get the same thing as PV followed by TA. Right? This is what we want to happen. Right? We want the matrix A such that this happens. Right? Right? In other words, so that TV coordinate vector with respect to F is the same thing as A times the coordinate vector of V with respect to E. Right? Okay, so here's what we're going to do. We let A be the matrix where AI, the ith column, as usual, the ith column is TVI's coordinate vector with respect to F. Okay. So I know there's a lot of things to remember, right? Like what is everything? What was the VI? Who are the VI? Does anybody remember? Montana?
The vectors
The basis of V, right? So you have this basis of V. So you take each. So if I want the first column, what do? I take the first basis element. I hit it with the transformation, and then I look at that guy's coordinate vector with respect to F. What was F? The basis of the target space. Okay, so I take each element in the original, take each basis element in the original space, map it over, and take the coordinate vector with respect to the target spaces vector basis. Okay, and those are the columns of my matrix. Okay. Don't worry, we'll do an example afterwards that will make this perfectly clear. Okay. So then observe. If I take QT of VI, Q of T of VI, well, that gives me T of VI's coordinate vector with respect to F. Right? Of course. That's just what it is. Right? Remember, Q is the coordinate vector map with respect to F. So I get the coordinate vector with respect to F of TVI. Okay. If I take TA of PVI, what happens? Okay, so something cool happens. What do you get? Anyone see it? Okay, I'll give 2 points on the exam to the person who sees the funny thing first. Yeah.
QWI.
QWI. What is W? Oh, W were the basis elements of that. QWI, let's think. QWI would actually be the ith standard basis element, right? The answer is no. So,
Okay.
yeah, no. Not kidding. Yeah, Tara? TW? Well, let's see. W. So, W, what's W?
It's the basis of, sorry.
Do you mean WI maybe?
Yeah.
Okay, so WI is an element of W, it's a basis element for W, but T doesn't act on W, right? So you can't say, it doesn't actually make sense. You can't say TWI. Yeah. T goes from V to W.
Okay.
Right.
Would you say the column vectors?
These are the column vectors of your matrix, yeah.
Yeah. So you get those.
Those?
Yeah.
So you're saying,
So I guess you go. I guess I'm just saying.
No, go ahead. You get AI, is that what you're saying? Yes.
Yeah.
Okay, so why do you say that? Why do you say that?
I mean, so P of VI is the same as VE.
The same as what?
Or like, bracket VE, right? And then, so you're hanging out with the transformation to, well, TA is like, are we saying it's the matrix, or I was thinking of it as the matrix?
Yeah, I mean, yeah.
Yeah, so A, yeah.
So yeah, the whole thing is A, V, I, E.
Yeah, and so, yeah, that gives you the common difference of yeah, so you're using matrix with the coordinate vectors, so, but that's already AI.
Eric, I'm sorry, I'm going to cut you off. Sorry. You're really close, but go ahead. You're
No, I was thinking
no?
wrong.
Anybody? Okay, so yeah, Mariah, you're really close. PVI is the coordinate vector of VI with respect to E. What's the coordinate vector of VI with respect to E? EI, the standard basis element, right? This is the standard basis element, right? And so what you get is TAEI, in other words, let multiply EI by the A matrix, right? When you multiply A by the standard basis element E sub I, what do you get?
Yeah.
You get AI, right? What is AI? AI is TVI F. Right, we made AI. We said AI was going to be TVI F. Yeah, Montana.
Is T sub A equal to A?
T sub A is the transformation that says left multiplied by A. Yeah. People tend to conflate them. So like, you say, oh yeah, but really this is a matrix, and this is the transformation that you get by left multiplying by that matrix.
Okay, so the left one's like a function.
Yes. Yeah, it's like the number 5, right? The number 5, you can have a function that says multiply by 5, right? Those aren't the same thing, right? Here's the matrix A, here's left multiplied by A. Yeah, Harry.
Was that a T before the VIF? The middle last VIF?
Is this a T?
Yeah.
Yes.
Okay.
Okay, so what do you see? You see that, right, TAPVI equals QTVI for all I. Right? But what does that tell you? That tells you that anybody see it? Right? We get agreement of these two things. We get agreement of these two linear transformations on the basis VI. And when you have agreement on a basis, then you have, they're the same, right? Remember this? We did this last time. Right? If you have two linear transformations that agree on a basis, then they must be the same. Right? So TAP actually does equal QT, right? Which is what we're hoping for. Right? We're hoping that TAP of B is QT of B for all B. Right? In other words, right? In other words, in other words, A of B with respect to E is TV with respect to F. Okay, so there is a matrix that embodies everything about the linear transformation. there is a matrix that embodies everything, all information contained in linear transformations action on this vector space. And that, the way you construct it is by taking the elements of your basis in your domain, mapping them through the transformation, and taking the coordinate vector with respect to the second basis and using those as the columns of your matrix. Okay. Right, so the matrix representation A of T with respect to E and F is constructed as AI equals T VI with respect to F, where E is V1 through Vn. So for example, going back to the example we did last time, the differentiation from P3 to P2, okay, we took 1x squared and 1x as our bases, right? What is the matrix representation of D with respect to E and F? What is the matrix representation with respect to E and F? So just take 1 minute and construct it. You just following this procedure here.
Just to double check, T of VI is WI, right?
No,
That's not.
it's not. It's not. Right? You've got some vector space.
Yeah.
You got one vector space over here. You've got another vector space over here. You've got a linear transformation. You've got arbitrary bases. Right? You've got one basis here and one basis here. There's no connection between these bases.
Oh, I guess I meant like, okay.
Right? You can change the bases. I could, here we're taking 1x squared and 1x.
Yeah.
I could have taken, 2 plus x, and 3x squared plus 5, or something like that. That's my first one. Yeah, you can change these bases as you feel. There's no relation between them.
I meant like not like it's part of the basis, but it's like, doesn't the transformation turn your vector into a vector in the other space?
Yes.
So then, isn't T of VI a vector in W?
It's a vector in W,
Okay.
yes, absolutely. But it's not the WIs.
Oh.
Right, the WIs
So
are up
it's
to you.
just W.
Yeah, you could call it W. It is a
It's just a
W.
random vector.
Yeah, it's some vector in your target space.
But it's okay, but that's also like the coordinate vector of that vector, because it's like the brackets.
Yes, yes. You're taking the coordinate vector of that with respect to the WI basis. Talk to somebody, and say, this is how you do it. Okay. Who wants to say? Who wants to say? How did you get it? Anybody? Other than Abel? Anybody? Montana, yeah.
I'm not sure if this is the transition example or just the coordinate matrix, but I got the first column is 1, 0, 0. The second column is 0, 1, 0.
So remember how you do it here. You say, okay, the first column, A1, I get by taking the first element of my basis here and taking the first element and hitting it with my transformation, and then take the coordinate vector of that with respect to f. Okay, so you take 1, you hit it with differentiation. Well, when you take the derivative of 1, you get 0, right? Right. So you get the coordinate vector of 0, the polynomial 0 with respect to f, right? And so what do? There, you say, okay, I want to express this 0 in terms of this as a linear combination, so it's going to be 0 is 0, 1, and 0 x's, right? So I use those coefficients, and I get 0, 0. Okay. And then for A2, should I let you do it, Montana?
Sure.
Yeah.
So we differentiate x,
Right.
which is 1, 0.
1, 0, exactly. Right? And then A3 is going to be differentiate x squared. You get 2x is coordinate vector. So what's that going to be?
0, 2.
0, 2.
I didn't realize the use of differentiation.
Oh, okay. Okay. Okay, great. So, so what is A? A is 0, 0, 1, 0, 0, 2, right? And you notice that that's the matrix that we used the other day. That's the matrix that we said, represented differentiation. Okay. Yeah, come on.
So, for just use it as an example, one with like the bracket 1f, it's the vector is 1, 0 because there's 1 in f and then 0 x.
Yeah, there's 1, 1 and 0 x's, right? So you take this 1, and this is not the number 1, but the polynomial 1, right? And you say, I want to express this 1 as a linear combination of these two polynomials. Well, it's 1 of the first guy, and it's 0 of the second guy, right? So I use those coefficients, 1, 0. Yeah, Montana.
How is this different from the transformation matrices that we did between vector spaces?
Last time what we did was from Rn to Rm. Okay, and this time we're doing it from an abstract vector space to another abstract vector space. So what we did last time was something more straightforward. We had Rn and Rm, and then we found a matrix that this thing actually equaled multiplication by that matrix. Okay, and remember how we did it? You take the standard basis elements and you map them over here, and you use those guys as your columns. Okay. Now this time we're going like this. We're saying that you have a vector space. Oops. You have a vector space, and you have a transformation between abstract vector spaces. You have bases, and you have the coordinate maps going down like this. And we're looking for a map that makes this thing happen. Okay, that's kind of different, but in fact it's actually really closely related. Okay, so yeah, you're actually hitting on something that I should have. But let me just take 1 minute. I wasn't sure if I wanted to say this or not, but since you've opened the door for me, I'm going to say it. Okay, so connection between the the first case, connection with the first case. Right? So the first thing we did was these matrix representations between Rn and Rm. Okay, so let me show you something kind of cool. Okay, so okay. So you remember how to get, if you're going from Rn to Rm, and you have some linear transformation, then the matrix you get, you take L of E1, L of E2, blah, 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 L of En, and that's the matrix that corresponds to this guy, right? That's the matrix that corresponds to this guy. Okay. So, we're going to do something cool, which is this. It's like, we're going to make this P go backwards. Okay, we're going to make this was an isomorphism, so we can actually go up. Okay, we can go up. And we're going to make a map from Rn to Rm. Okay, here it is. First, go up through P inverse, then go across through T, and then go down through Q. Yeah.
You said you couldn't go from. Oh no.
You can't go back. You can't. This T doesn't go that way.
Yeah.
Yeah, fine.
What are P and Q?
So P and Q were the coordinate maps, right? So P of remember P of P of V was the coordinate map with respect to E. Q of W was the coordinate. I'm sorry, the coordinate vector of W with respect to F. Okay, so notice this thing maps from Rn to Rm, right? It goes from Rn to Rm. Who am I talking to? I'm talking to Montana. That's right. Okay. Okay. So, what's the A for it? What is the A for it? What is its matrix representation? Like, what is the A? What's the A for it? It's going to be QTP inverse E1, QTP inverse E2, QTP inverse En. Right?
Isn't that just
No. Okay, so there's something funny that happens. Okay. Do we have time? Yeah, okay, so I'll give 3 points to the person who sees the punchline, sees the funny thing here, the cool thing that happens. It's a cool, I don't know. So I'll give you 1 minute because we don't have that much time. P is the coordinate vector map. Like takes your vector to its coordinate vector.
Yeah. Wait, can P be represented as a matrix?
No, because V is not a Euclidean
So it's
space.
like a
It's a linear transformation. It's an isomorphism, actually.
Okay.
A one-to-one onto linear transformation.
And because
So it's
we're not
invertible.
We're not in Euclidean space, so like it doesn't have to be represented as a matrix.
Right.
Yeah.
Eric.
Could you take QTP inverse out of the vector?
No. Selling.
Well, QTP inverse equals L, right? Or is that? Could
You can call it L.
no, like the the L you made? Is that what it means?
I mean, it's L is just, there is no L. I mean, L didn't have any meaning. L was just some linear transformation. So it is some linear transformation, but yeah, just calling it L won't get you, I'm afraid won't get you anywhere. Montana first.
Just the basis for Rn.
No, Mariah?
I mean, I was gonna say, you could say that T is like A, right? So, and then A times Q1 is like the coordinate vector. Yeah, it's like similar to what we were doing before. Like
You're not far off.
Q times Q1 is, I guess,
Okay, I'm sorry, Mariah.
Sorry.
I'm gonna have to cut you off. But, okay, so what's P inverse of E1? What? V1. V1, right? So what do you get? Right? QT P inverse EI is QT of VI. Right? So in other words, you get TVI coordinate vector with respect to F. Right? Which is the same thing as the A we had before. I've erased it. The same thing as this A, right? You get TV1, TV2, TV, and F, which is the matrix representation of T with respect to E and F. Okay. Don't worry about it if this, I wasn't even planning to include this fact, but if you don't get it, that's fine. If you get it, that's great. The point, let me say the point. Okay, the point is just that if you look at this map going like this, and you look at the matrix that represents that, that's the same matrix that makes the diagram commute. Okay, that's the same matrix that makes the diagram commute. Okay, don't worry about it if that didn't make any sense. Okay, let's go on to the last idea in the section, which is change of base as well. Let's say matrix representation of T going from R to Rm with respect to different bases. Okay. Okay. So let's remember something first. Okay. So first recall that if B being B1 to Bn was the basis of Rn, and V was a vector in Rn, then the coordinate vector of V with respect to the B basis you could get by taking your vector and then multiplying it by the inverse of the matrix that you got from taking the basis elements as columns. Does everybody remember that? Does everybody remember that? The way we got this fact, in case you've forgotten, remember. If you multiply on the left, what this is saying is that V is this linear combination of the columns, right? V is the linear combination of the columns with these guys as the coefficients, right? So the way you get the coefficients is by taking a vector and multiplying by the inverse matrix, right? I think everybody remembers that. Okay, so suppose we have two bases. E equals V1 through Vn of Rn, and F being W1 through Wm of Rm. Okay. Then we can do what we were doing before. We can do what we just did. You have some, to get a matrix representation of some linear transformation between Rn and Rm with respect to the new bases. Sorry to write too quickly. When I was an undergraduate, I really admired this one professor who could write as fast as he talked. And this is the result. I read quickly. Okay, so what are we saying? Remember the first thing we did. You have a linear transformation between two Euclidean spaces, and you got some matrix that actually T sub A equal T. Now we're saying something a little different. You have two bases, E and F of Rn and Rm, and we're going to take the matrix representation. Right, we're going to take the matrix representation. So you've got your T going like this. We're going to take the matrix representation now. Okay, that'll give us a different A. That'll give matrix representation with respect to those bases. That'll give us a different A. Right? What's the A? What's A? What's A? Well, remember, AI is going to be TVI with respect to the F basis. Right? The coordinate vector of TVI with respect to the F basis. Okay. But this is easy now. Calculating the coordinate vector is easy for the Euclidean spaces, right? You just take W1 through Wm and invert it and multiply TVI by it. Okay, so we get a different matrix representation of T. Right? We get a different matrix. It's a matrix representation with respect to some different bases. Okay. Now this may seem kind of funny, but what's really going on is that this original thing that we did, finding the matrix representation over here, finding that matrix A, that was actually with respect to the standard bases on both sides. Okay, and now what we're seeing is that you can do it with respect to some other bases. Okay. Let me just quickly do one example. Sorry to hold you. Quickly do one example. This is related to your Markov chain example. Okay, so let M be 0.94, 0.06, 0.02, 0.98. Remember this guy? This was the transition matrix for the city and suburbs problem. Okay. Let U1 be 1, 3, and U2 be negative 1, 1. Right? You remember that M of U1 turned out to be U1 itself. Right? And M of U2 turned out to be 0.92 of U2. Right? These guys turned out to be eigenvectors. When you multiplied it by the matrix, nothing happened. When you multiplied this guy to the matrix, it got multiplied by 0.92. Okay. So the matrix representation of, so let's call this basis U1, U2, U. The matrix representation of T sub M with respect to U and U on both sides is going to be as columns A1 is going to be 1, 3, negative 1, 1 inverse times MU1, and A2 is 1, 3, negative 1 inverse times MU2. Right, that's this thing here. And we're taking our basis and we're inverting it. Right? We take our basis elements, put them in a matrix, invert it, and multiply by MU1 and by MU2. We use those guys as their columns. Yeah, column.
What does the top line read?
The matrix representation of T sub M with respect to U and U. So U is the basis. We're going to use the same. This is like E and F. Those are our E and F. Right? A turns out to be 1, 0, 0.92. So it turns out to be this matrix 1, 0, 0.92. Okay. And so the point is this, that the point is this, that up here with respect to the standard basis, the behavior was hard to understand. Right? Multiplying by this M, what does it do? But if we take the matrix representation with respect to a different basis, the behavior becomes easy to understand. Okay. The behavior is, the linear transformation's behavior is simple when you change the basis on it. Okay, I'm sorry to rush through it. I'll try and talk a little bit more at the beginning next time.